Hi! In this problem, we're going to find an unbiased estimator for the variance of a random variable. Suppose random variable x has some unknown mean theta and some unknown variance v. We're going to use some IID observations of x, x1 through xn, and combine these observations to find an estimator that will estimate theta and v. Now, how do you know that if an estimator is any good? For example, here's a bad estimator. If I'm trying to estimate what theta is, I could come up with an estimator that takes in these observations but ignores them and always just spits out 0 as the estimate for what the mean is. So that estimator is probably not very good. So how do you know if an estimator is good? Well, there's some properties of estimators that are desirable to have. One of them is for the estimators to be unbiased. So an estimator capital A of some unknown parameter little a is unbiased if the expected value of this estimator is equal to the parameter that you're trying to estimate. Remember that in general, an estimator is a random variable because it's based on some random observations. So it won't always be equal to, it won't always give you the value that you're trying to estimate, but if it's unbiased, then you know that on average, it'll give you the right value. Let's practice first on the mean theta and see if we can come up with an unbiased estimator for it. One proposal is the sample mean. Let's calculate the sample mean as the average of all the n IID samples that we get. So you take x1, add up all the xi's and divide by n, and we'll call that mn. So in order to verify that this is in fact unbiased, all we have to do is calculate the expected value of mn and verify that it's equal to theta. The expected value of mn, in order to calculate it, will rely on linearity of expectations. So the first thing we can do is we can pull out at 1 over n, and then in order to calculate the expectation of the sum by linearity again, that is equal to the sum of the expectations. And so what we get is it's expectation of x1 plus all the way through expectation of xn. Because x1 through xn are all IID observations of x, they all have the same mean, which is theta. And so it's 1 over n times n copies of theta, which gives you that the expectation of mn is in fact equal to theta. And so we've shown that this is an unbiased estimator of the mean. Now let's try to take that and see if we can find an unbiased estimator for the variance v. And here is one proposal. Let's let Sn hat squared be equal to this expression. Now let's see what we're doing here. We're taking each sample xi, subtracting the sample mean, squaring it, and then taking some sort of average of those. And this seems like it may be a good choice because this is kind of like what a variance calculation does. You take the square deviations from the mean and take some sort of average of those. So let's see if this is actually correct. And in order to do that, we'll do the same thing that we did for the mean, which is we'll calculate the expectation of Sn hat squared and verify that it's equal to v. First, let's try to simplify this expression a little bit. So we can expand this square, and we'll get xi squared minus 2xi times mn plus mn squared. And next, let's distribute this summation. So we'll split it up into 3 different summations. The first one adds up all the xi squares. The second one adds up all the xi's. So we can pull out the mn outside of the summation because mn does not depend on the summation index I. And lastly, we have a summation of mn squared. And just like for this case, mn squared also doesn't depend on I. So we just have n copies of mn squared. And now let's look at this middle expression here. Well, we know that the sum of the xi's is actually just equal to n times mn. So let's substitute that in to try to simplify this even more. So the sum of the xi's is equal to n times mn. So we have 2 times mn times n times mn, which gives us 2 times n times mn squared for that. And now we also added n times mn squared. And so what we're left with is just minus n times mn squared. So we've simplified this expression a little bit. And now if we were to try to calculate the expected value, we know that we're going to have to rely on linearity of expectations again. And if we look forward, we can see that what we're going to have to calculate eventually is the expectation of xi squared and the expectation of mn squared. So let's calculate those first. What is the expectation of xi squared? The expectation of xi squared, we can write that as the variance of xi plus the expectation of xi quantity squared. Now, what is the variance of xi? The variance of xi is v. What is the expectation of xi? The expectation of xi is theta, and we square that, so we get that this is equal to v plus theta squared. What about the expectation of mn squared? The expectation of mn squared, we can do a similar thing, and this is equal to the variance of mn plus the expectation of mn quantity squared. But we don't know what the variance of mn is yet, so let's try to calculate what that is. The variance of mn is the variance of the sample mean, right? So it's the variance of 1 over n times the sum of all the xi's. Now we know that 1 over n is just some constant, and when we pull it out of the variance, we have to square it. So we get 1 over n squared times this variance, the variance of the sum of the xi's. But because the xi's are independent, the variance of the sum isn't actually equal to the sum of the variance. So what we get is the variance of x1 plus all the way through the variance of xn. Now, all of these variances are equal to v. And so we get n times v divided by n squared. And that gives us v over n. Now, what is the expectation of mn? Expectation of mn, when we calculated it earlier, we saw that it actually is equal to theta. And so we can fill this in now. The variance of mn is equal to v over n. And the expectation of mn is theta. And you square that, you get theta squared. So now we know both of these expectations. So let's calculate the actual expected value of this estimator. Sn hat squared. So like we alluded to earlier, it's going to use linearity of expectations. So the 1 over n minus 1, we can pull that out. By linearity, we have that this is just the sum of the expectation of all the xi squares. And then we have n times the expectation of mn squared. We still have the 1 over n minus 1. We calculated the value of expectation of xi squared. It's equal to v plus theta squared. That doesn't depend on I, so we just have n copies of that. So it's n times v plus n times theta squared. We know also the expectation of mn squared. It's v over n plus theta squared. We multiply that by n, and we get v plus n squared. And we subtract, so we get minus v minus n times theta squared. These cancel. N times theta squared cancel out. You get a nv minus v, which is n minus 1 times v. The n minus 1 cancels out with the 1 over n minus 1. And so in the end, you get that this is, in fact, equal to v. The expectation of the estimator is equal to v. And that shows that this estimator is, in fact, an unbiased estimator of this variance v. So I hope that was helpful, and we'll see you next time.